Thanks. Yes, thanks so much for the organizers for inviting me. Well, I'll tell you about sort of local weak convergence, which is, I guess, another way of saying sort of Benjamini-Schramm convergence for sort of solutions of random constraint satisfaction problems. So what do I mean by that? Well, constraint satisfaction problem basically means what it sounds like. You have a set of variables and some collection of constraints, and you want the variables to satisfy the constraints. So think like solving some system of equations, coloring a graph, satisfying a Boolean formula. And because we do probability, we'll pick the constraints randomly. And so these will be random constraint satisfaction problems. Just to fix some examples in mind of this, I think maybe the conceptually nicest examples are sort of combinatorial properties of random graphs. So imagine you have your favorite sparse random graph, maybe an Erdős-Renyi random graph or a random deregular graph. And you can ask, can you sort of k-color this vertex? So here the colors of the vertices are the variables. The edges are the constraints, saying that neighboring vertices have to have different colors. And because we pick the edges randomly, it's a random constraint satisfaction problem. Or you could ask, is there a large independent set of the graph, say? Another type of CSP are sort of Boolean formulas. And the canonical sort of random example of this is the random k-sat model. So you have n variables. They are each either true or false. You think of them, which I'll write as either plus or minus. And then our constraints will be formed by taking k of the variables or their negations and taking the or of those. And then you just pick those uniformly at random. And then you pick m clauses, and you want them all to be satisfied, so you take the and of them. So you get a sort of random Boolean formula. So a clause is something like x3 or x4 or not x5. And then a solution to the constraint satisfaction problem would just be an assignment of the variables so that the formula evaluates to true. Okay, and those are called solutions or satisfying assignments. And so the more constraints you put on something, the harder it is to satisfy them all. So we can parameterize things by the constraint density, the ratio of the number of constraints divided by the number of variables. I'll call this alpha. And so finally, the model that I'm actually going to prove something about is what's called the not all equal sat model. It's a variant of random k-sat, where you ask that both x and the negation of x evaluate to true in the formula. Or equivalently, in each clause, at least one of the terms evaluates to true, and at least one of the terms evaluates to false, and hence the not all equal name. This has sort of, all of the models I've mentioned so far have very similar qualitative features. But this not all equal sat one has sort of some extra symmetries, which make it essentially the most tractable in this group. And to make it, and another variant you can impose is also to ask that it's regular, in the sense that every variable is in the same number of clauses. And so this is sort of the analog of asking about a random deregular graph rather than an Erdős-Renyi random graph. Okay, so all of these models essentially are living on an underlying graph. For colorings of random graphs, it's obvious what the graph is. For the Boolean formulas, you can take the formula and construct a sort of bipartite hypergraph. So on one side of the graph, you have a vertex for every variable of the graph. On the other side of the graph, you have a vertex for every clause, and you just connect the clause to the variable if that variable appears in the clause. And I'm also going to decorate them with either blue or yellow, depending on whether or not they're negated. Okay, so because we chose the clauses randomly, we get a random graph, and like most models of random graphs, it's locally tree-like. So there's very few short cycles in the graph, and if I just pick a vertex at random, its local neighborhood will look like a tree. So actually, the Benjamini-Schramm limit of these graphs are very simple to understand. It's just sort of a hypergraph branching process tree, or in the regular case, just a regular hypergraph tree, or sort of the infinite tree. So the question I'm going to be interested in is when we sort of decorate the variables with the values of a random solution to this problem. And so ask sort of what the graph with the vertices labeled by a random solution look like. And we'll want sort of the local weak limit of that object, which I'll define in a few slides' time. So in terms of what sort of questions you can ask about random constraint satisfaction problems, the first is just what, when are there solutions? What density of constraints can you sort of manage to satisfy all simultaneously? This is sort of well understood for at least several of these models now. And once you know that, you can ask sort of more detailed questions like, how many solutions are there? Can you algorithmically find a solution? And for today's talk, sort of what does the local weak limit of one of these solutions look like? So what does it look like locally? And to begin with, I just want to do some sort of simple calculations to get a sense of what these models look like. So let's say we take the nodal equal sat model, and I'll just write Z for the number of solutions you have. And this is something that you'd at least hope that you're even an undergraduate in your class could calculate, maybe optimistically, but because there's 2 to the n possible ways of assigning the variables. Each clause can be satisfied independently with probability 1 minus 2 to the minus k minus 1, and there's m of them. So this is just the expected number of solutions. It's something that's sort of growing exponentially. It's in n, so it's like e to the n times some constant that depends on alpha in a sort of linear way. And so there's some density alpha in which this exponent is 0. Let's call that alpha 1. And at that point, you go from having, in expectation, an exponentially growing number of solutions to the expected number of solutions going to 0. So certainly by Markov's inequality, that's an upper bound on the satisfiability threshold when you have solutions. But it turns out that it's not the satisfiability threshold, it's an overestimate. And that's because essentially solutions have, if you have one solution, you can find a lot of nearby solutions. So there'll be a constant fraction of variables that aren't in any clauses at all. So if I took one of those variables, so if I had a solution, those unconstrained variables could be just flipped to anything else. So if you have one solution, you have at least 2 to the epsilon n solutions. And so Markov's inequality would give you a slightly better bound as a result of that, which still wouldn't be the right upper bound. There's also variants of this argument that work for the regular case. So generally, this won't give you the right upper bound. Okay, but it's actually quite close. It actually does quite well in a lot of these models. So how could you find a lower bound? Well, the first moment method is good for upper bounds. The second moment method is good for lower bounds. So if you can bound the probability of having a solution by the ratio of the first moment squared over the second moment. So, of course, this only gives you something meaningful if they're sort of comparable sizes. For nodal equal sat and the coloring model, these were the second moment method works up to our upper bound on the satisfiability threshold minus a constant. So in nodal equal sat, this is growing like 2 to the k minus 1. And the difference between these two thresholds is just a constant that's sort of independent of k. So it doesn't exactly tell you what it is, but it pretty well narrows down sort of the location of the satisfiability threshold. On the other hand, for random k-sat, the second moment method in its, at least the vanilla application of it, never works. So it doesn't give you anything for any density constraints. Okay, but suppose, suppose the second, the second moment method can, tell you that there are solutions, but it can also tell you a lot more than that. And so suppose we were wanting to generate a pair of the graph chosen at random, and then a random solution on that graph. So the right way to do that is you pick the graph uniformly, and then pick the solution uniformly given the graph. But you could sort of mix things up and do it the other way around. First choose the solution, and then pick the graph given the, uniformly given the solution. So some elementary conditional probabilities will tell you these are not the same thing. The second one is called the planted model. You plant a solution, and then pick the graph given that solution. And that's actually a lot easier to work with for a lot of things. But they're not the same. And the reason why they're not the same is that essentially graphs with, say, a lot more solutions will be chosen more often in the planted model because there's more solutions that give rise to them. So essentially you end up with a size bias distribution over, for the graphs. Okay, so these distributions could be very different. On the other hand, if the number of solutions was pretty much the same for every graph, then they wouldn't be very different. If you size bias things that all have the same size, then you're not doing anything. So if the second moment worked sort of perfectly, and the second moment was more or less exactly the first moment squared, then you'd basically just get the same distribution back. And the two models would be contiguous. And if you could prove things about the planted model, you could prove things about the original graph as well. So this isn't generally true for any of these models. What's generally the case when the second moment method works is that the second moment divided by the first moment squared will converge to a constant that's strictly bigger than 1. And the reason for that is that there's some additional variance in the number of solutions of these problems. And that comes from essentially the fact that if you add an extra, say, 3 cycle in the graph, that will change, say, the number of colorings you have in the graph by a constant multiplicative factor. And the same for 4 cycles and 5 cycles and so on. But if you condition on how many 3 cycles and 4 cycles and 5 cycles and so on that you have, then you can essentially eliminate this variance. And there's a machinery for doing this called the small graph conditioning method, which lets you say once you've conditioned on how many small cycles you have, then the number of solutions is essentially concentrated. And as a consequence of this, the planted model and the original one are contiguous. So if you can prove something with high probability in the planted model, you can also prove it in the original one. Okay, so, and this is useful for understanding what sort of the local distribution looked like. So imagine we were doing colorings of random graphs. If we were doing this in the Erdős-Renyi setting, we just pick a random coloring. So I'd label some of the vertices red, some of them blue, some of them green. And then I have to add in edges uniformly, but conditional on this being a coloring. So that will just mean that I can connect vertices with different colors, and I just can't, I'm just not allowed to connect up 2 vertices of the same color. And so this is a, and so then you can sort of analyze what the local neighborhood of a vertex will look like. You can also do this in the random regular case. It's a little bit more complicated, and it's better if you first condition on sort of how many vertices you have of each color, but something even a little bit stronger, how many edges you have going between each pair of colors. So how many edges that connect green and red, green and blue, blue and green edges. Now, in this case, it's not surprising that sort of the having a distribution of these that are sort of essentially uniform between all of the allowable possibilities is the one that makes the dominant contribution to that. And then if you want to build the graph, then you just sort of take, for each green vertex, you connect it to the D of the edges with a sort of, all the parts that are matched green, and the red ones you match to sort of the red ends of edges. And so you can construct this according to a configuration model. So you're just taking a uniform matching between sort of green vertices and green ends of edges. And so if you do that, then it's you can relatively easily understand what the graph looks like around a fixed vertex. So suppose I pick a blue vertex. It's connected to some D randomly chosen blue ends of edges. The other sides of those will be basically equally likely to be red and green. So in the local neighborhood, you'll have D children, and each will be equally likely to be red and green. Now, they're not, on a fixed graph, the colors of the neighbors are not quite independent, but asymptotically, as the size tends to infinity, they'll be independent. And so the distribution that you get in this local neighborhood will look like a simple Markov model where the root is just chosen as a uniform color, and then each child has a uniform color conditional on it being different from its parent. And so you can just sort of propagate that coloring down the tree. And so this is the example for colorings, but essentially any sort of constraint satisfaction problem or spin system on a random graph, if it's planted model, if there's sort of a single empirical distribution of that's sort of dominant, then the distribution you get around a randomly chosen vertex will look like a Markov model on a tree. Yeah.
Here you're talking of the planted model, and you're also looking at the local statistics of the planted solution. I guess you could take the planted model and choose a uniformly solution and look at the local statistics of that, or that doesn't make sense, or it's the same?
I think by reversibility that should be the same, yeah. Yeah. So this, okay. Now I was also saying, talking about this with respect to like one vertex chosen in the graph, what its local the colors in its local neighborhood look like. But I could pick sort of several different vertices and look at the joint distribution of the colors in their neighborhoods. And as long as I don't pick too many of them, those will be also asymptotically independent as n tends to infinity. And so what that says is that the empirical distribution of colorings in local neighborhoods will be concentrated around this Markov model. Okay, and that's a statement, that's a with high probability statement. So it's one that you can transfer back to the original model. So in the original model also, if I pick a vertex at random, look at its local neighborhood, after averaging over everything, it will look like this Markov model on the tree. Okay, and this is essentially a sense of local weak convergence for the coloring. So let me be a bit more specific about what I mean by that, because you could define this in multiple ways. And so generally, generally when you talk about local weak convergence, you mean what is the local graph structure around a randomly chosen vertex. So I want to talk about sort of the local graph structure and coloring or spins. And if I do it in the regular case, actually, the graph structure will always be the same. It will just be a regular tree. So really, I'm just interested in the limit of the distribution of colorings around a random vertex. And so I want to describe what that means to converge to some coloring or measure over colorings on the regular tree. So one definition, which we call convergence locally on average, is that if I pick a vertex at random and for some radius r, average over the graph and the choice of the vertex and look at the distribution of colors there, that's close to the distribution of nu on a ball of radius r. A stronger notion of convergence would be to say we pick a vertex at random, condition on the graph and the choice of vertex, and given that, look at the distribution of colors in its local neighborhood, and ask that on average that's close in total variation distance to nu in a ball of radius r. So this second one, convergence in probability locally, is a strictly stronger property. Now the kind of sketch I gave on the previous slide implies essentially convergence locally on average, but actually the stronger version is also true. But sort of essentially, if the second moment method works, then you can sort of nail down that most vertices in the graph will have their local, the distribution of the spins locally around that will look like the corresponding Markov model. Okay, so now you might say, okay, this is like a simple theory for telling you what local neighborhoods look like, but it's under the assumption that the second moment method works, and that doesn't work all the way up to the satisfiability threshold for these models. You could say maybe this was just a technical assumption that we needed in order to show that the planted model was contiguous with the original one, and that it's not very important. Okay, well, suppose we were doing this again still for colorings on random graphs. So the limiting, so the Markov model we get on the infinite deregular tree has an interesting phase transition when the degree is bigger than k log k, in that most vertices are frozen, in the sense that if I pick a random coloring, and now I want to and the root is, let's say, red, and I want to change it to blue. Most of the time, you'll have to change the colors of an infinite number of other vertices in order to switch the root from red to blue and still have a valid coloring. There's no way of doing it sort of just with some local changes. On the other hand, a constant fraction of one's vertices aren't frozen. There'll be some vertices that are, say, only next to green vertices, and they could be either red or blue. Yeah.
You say you pick a uniform coloring, so how exactly? This is the infinite tree.
So this Markov model on the tree where our sort of candidate for the local weak limit. Okay, so there's a small fraction of the vertices that are free in the sense that you can change them from, say, one color to another with only local changes. Okay, but this is a local being free is sort of a local property. So if this was the local weak limit, then you'd also have the same density of free variables on like the random deregular graph. Okay, but then from that you could sort of work out how many ways there are of changing these free variables to get other nearby colorings. And so you could say for a typical coloring, how many nearby other colorings are there? And the problem is, at some point, there's too many of them. So as you get close to the colorability threshold, the number of nearby colorings exceeds the total expected number of colorings of the graph, which which is bad. So so that's a contradiction to the Markov model being the local weak limit. So there has to be something happening as you get close to sort of the colorability threshold that's sort of breaking this very simple local weak limit as being the right thing. Okay. Okay, so for the next part of the talk, I'm going to describe how physicists look at these models and how they would sort of come to tell you what the right local weak limit should be. Okay, so this is a digression into physicists sort of the physics picture of how to study these random constraint satisfaction problems. You can think of they think of the solutions as being sort of split into clusters of solutions. So I can think of two, say, colorings of a graph as being adjacent if they just differ at a single vertex, or maybe at a small, just in a small number of vertices. And so if I have a notion of adjacency, I can talk about connected components of colorings, and then these, circles are meant to represent, those connected components. And there's a series of phase transitions as we increase the density of constraints, or the average degree of the graph. So when the average degree is low, all or almost all of the colorings should be in one single component. But at a certain threshold, it breaks into exponentially many clusters, each with an exponentially small fraction of the total number of colorings. But in both of these regimes, the local weak limit should still be the nice Markov model. But there's another threshold called the condensation threshold, much closer to the colorability threshold, where things change. Here, there's still, in the condensation regime after that, you still get clustering of the colorings, but the biggest few clusters have almost all of the colorings in them, or almost all of the solutions. And this is the regime in which you get a different local weak limit. And it's like closely connected to the fact that you get the coloring. This is also the regime in which they would call it replica symmetry breaking, which in this sense just means that if you pick two solutions at random and look at how close they are together, then there's really two possibilities that come up. One is that you pick them in different clusters and then they look basically orthogonal to each other, or you pick them in the same cluster and then they look very similar to each other. And then the final transition is sort of the satisfiability one, after which you have no more solutions. Okay, so So this sort of describing clusters as connected components of solutions doesn't sound like a very tractable way of thing to analyze, but actually there's a nicer sort of combinatorial representation of these clusters. So I'll describe it in the case of say, the not equal sat model, but there's an analogous one for colorings, which is a little bit more complicated. So start with just a solution. So every vertex is either plus or minus. And now I want to sort of explore this cluster. So some of the variables I could flip between plus and minus without violating any of the constraints. I'll call these ones free, and I'll mark them with an F rather than a plus or a minus. And then setting some variables to free might mean other variables could also be set to free. So if they're in the same, so then I'll sort of iterate this process until I've sort of set everything to be free that can be set to free. And so I'll get a configuration where everything is plus, minus, or free. And it turns out that this will map the whole cluster down to a single point. Okay, more or less. And moreover, what you get in the end has to follow a few rules. So it's itself a random constraint satisfaction problem. So because of how we arrived at it, every free variable can't be sort of forced by any of the clauses it's in. On the other hand, every frozen variable, the pluses or minuses, has to be forced by at least one of the clauses, otherwise we would have set it to free, and none of the clauses can be violated. Okay, so we call this model the frozen model, and it's essentially a way of a combinatorial encoding of the clusters of solutions of the random constraint satisfaction problem. So we've gone from one random constraint satisfaction problem to a more complicated one. So you say, why is that making progress? It's because this one has sort of additional rigidity. If I look at this model on the infinite tree, it has a sort of rigidity in the sense that to go from one valid configuration to another valid configuration, you have to change an infinite number of variables in order to do that. So there's no sort of local changes that you can make. And on the graph, the consequence of this is that typically to go from one valid frozen model configuration to another, you have to change a linear number of the variables. So there's no additional clustering in the frozen model. And so the original model has clustering, but not clustering of clustering. So it's just a sort of simple one level of clustering. Okay. And so now I want to sort of look at the condensation regime specifically and break down the expected partition function according to cluster sizes. So we'll sort of arrange the clusters in order of size and look at the contribution made for clusters of size e to the ns and make a completely unjustified assumption that the number of clusters of size e to the ns is given by e to the n times some sigma of s, where sigma is the cluster entropy function. So no justification that such a function should exist, but it would be useful to sort of calculate what would happen if it did. Okay, so then since these are on sort of exponential scales, the biggest contribution has to come from the s that maximizes s plus sigma of s, or equivalently the point where sigma has derivative -1. Okay, so this is sort of what the picture would look like if we're in the clustered regime. As you increase the constraint density, the number of solutions will tend to decrease. The condensation threshold will be the point at which this tangent point lies on the x-axis. The condensation regime, it's sort of strictly below the x-axis. Then the satisfiability threshold is the last time that you have any solution, so when the maximum of sigma is 0. And then after that, you don't have solution or clusters of solutions of any size. Okay, and so we specifically want to understand what happens in the condensation regime. So here, the size s that makes the biggest contribution to the expected value has a negative value of sigma, meaning that the expected number of those clusters is, exponentially small. So in particular, you don't expect to see those at all in a typical solution. So the main contribution to the expected value doesn't happen. And so typically, the number of solutions will be much smaller than the expected value. These are also the clusters of this size are also the ones that look like the solutions in them look like the Markov model. So those also don't appear exactly because they have a negative value of sigma. So what solutions do appear? Well, you take the biggest value of sigma, which is greater than or equal to 0, so the largest root of sigma. And the prediction is that this tells you the largest cluster size. And because sigma is 0 at that point, you expect to see sort of just order 1 of them. And that's why you have this prediction that you see that most of the mass is just on a constant number of clusters. Okay, so just to summarize, if we knew the value of, if sigma existed and we knew what its value was, we could read off all of the thresholds that we'd be interested in. And there's been progress in a range of these models over the years of proving various of these predictions in various different models. But there's a lot of blank spaces in this as well. Because there's lots of combinations of different models and regular or not, and yeah, we've sort of only done the nicest, easiest ones so far. Okay, but how would you calculate sigma? Well, the sort of exponential growth rate of the expected value of the number of solutions tells us something. It tells us sort of the maximum of S plus sigma of S. If I worked out the expected number of clusters, this would also tell us something. It would be its exponential growth rate would be sort of the maximum of sigma. The point, if I wanted some other point where the derivative was, say, minus lambda, I would want to sort of maximize lambda S plus sigma of S. And so what this corresponds to is calculating the expected, or summing up clusters to the power of lambda and taking the expected value of that. And if you could do that for every lambda, you would essentially be computing the Legendre transform of sigma of S. And if you are willing to believe that sigma is concave, as I've drawn it, then you'd be able to sort of invert that and work out sigma. Okay, but this looks like a terrible thing to do because you're sort of grouping solutions into groups and then raising them to a non-integer power and then adding them up and trying to take the expected value of that. But actually, it's not as bad as it sounds because you can essentially write this frozen Z lambda as the frozen model with extra weights on the free variables. Okay, so if you want to know the size of a cluster given by the frozen model, it's essentially the number of ways you can assign values to the free variables in it. And the free variables will tend to be fairly rare. There'll be a forest of small subcritical branching processes. So you just need to sort of multiply how many ways there are to fill in the free variables in each of those trees. So we could sort of write a equivalent but more complicated model where the free variables know what sort of tree of free variables they live in and where they sit in that. And then there's a canonical way of writing weights so that if you multiply all the weights within a tree, you get the number of solutions for that tree. And if you multiply all of the weights in the whole graph, you get the size of the cluster. And then if you take these weights to the power of lambda and multiply them all together, you get the size of the cluster to the power of lambda. And so this gives you a sort of weighted random constraint satisfaction problem. And then you just want to work out the expected partition function of that. Okay, so, and then this gets to the topic of how do you work out sort of moments of partition functions of spin systems on random graphs. And well, for random regular graphs in particular, you can just sort of calculate or work out the contribution for a particular sort of empirical distribution on the edges. So I'll call this mu. Once you fix that, so this is like the number of edges between red vertices and blue vertices in coloring, say. Once you fix that, then it's sort of a configuration model. You end up with ratios of multinomial coefficients and products of some weights. And after applying Stirling's formula a bunch of times, you get e to the n times some function of this empirical distribution. And then you just need to maximize that over empirical distributions. And it turns out that there's a way of doing that in terms of solving sort of fixed points of certain equations called belief propagation equations. I won't go into that, but and you can sort of work out what the moments of this weighted partition function are. So now there's a bit of a wrinkle to this, which is that this formula only really assumes that you have a finite number of possible spins. But actually, if I allow spins to be sort of, what type of tree of free variables you are, the trees of free variables could be of unbounded sizes. So that's sort of a unbounded state space. Okay, so with Nike Sun and Yumeng Zhang, we were able to sort of control that well enough to work out the size of the partition function to a sort of e to the little o of n factor, which is enough to work out the exponential growth rate of the number of solutions in this condensation regime. But that's not enough to answer more detailed questions. So you really want to work out the partition function up to a sort of constant multiplicative function, or like an order 1 factor. And so with Danny Nam and Yongtak Sun, a few years ago, we were able to sort of do this, where essentially we have to be able to sum over all the possible free trees, or all the possible ways that the variables could form free trees. But if you do this, you can show various things, and in particular that most of the solutions are just lie in a few big clusters, but also that the biggest and second biggest clusters are of like a comparable size. And then extending this with recently with Yongtak, we could also give a description of what the local weak limit looks like. And essentially, it's another sort of configuration model description. You can sort of write down what's the but not for the solutions, but for the clusters. So you can write down what fraction of frozen pluses and minuses you have, what fraction of free variables are in trees of different sorts, and what fraction of the time each type is next to each other. And then you can construct a configuration model out of these and work out the local weak limit of that. And then in order to sort of make this about solutions rather than the frozen model, you then fill in the free trees just uniformly, and they're all finite, so you can do that. So this is convergence in the weaker sense of local weak convergence. So converges locally on average. It doesn't, convergence in the stronger sense is not true, because, and that's essentially because what the distribution in a particular variable will look like will depend on sort of what the dominant few clusters look like around that particular vertex. So some of the time, so for some variables, they'll just be, almost always a plus. other variables will be sort of equally likely to be plus or minus. Okay, and also I should say the model you get is not Markovian. It's and essentially it's like the original Markov model, but reweighted to have fewer local colorings nearby. Okay, so this was a very vague description of what the limit is. If you, a more concrete one looks like this, but maybe I'll end here instead of walking you through. Like I had to choose the tiny, like the /tiny font on fit everything in. But anyway, thanks for listening.